Math 8, Unit 5, Functions, Lesson 3. Function notation using multiple representations. All right, I'm going to go through a few different representations you can see a function in and talk about how to use function notation for those things. First, with an equation. Here we have the equation f of x defined as 13x minus 7. What we will do when we evaluate something from an equation, we will plug in the value for x from whatever's in the parentheses and then evaluate. So f of 3 will be 13 times 3 minus 7, plugging in a 3 for the x. This is 39 minus 7, which is 32. F of 0 is going to be 13 times 0 minus 7, plugging in 0 for x. That gives us 0 minus 7, negative 7. F of 10, this is going to be plugging in 10 for x. So 13x is 13 times 10, and then minus 7. 13 times 10 minus 7 is 123. F of minus 1, we're going to plug in negative 1 for x. So 13 times x minus 7 becomes 13 times negative 1 minus 7. I like to put parentheses around anytime I plug a negative in to help me avoid making errors. Anyway, negative 13 and negative 7 do make negative 20. From a mapping diagram, you're going to find your input and look for the corresponding output by following the arrow. Now these are linear equations, so we can use linear relationships, linear patterns, to find missing values. T of 5, we find the input of 5 and find the output that it goes to. T of 5 ends up being negative 2. T of 1, we find the input of 1, the output that goes with it is 10, so T of 1 is 10. T of 3, here's the input 3, the output that goes with it is 4. Now T of 7, there's a common mistake that might occur here where a student would think that it is 2 because there's a 7 right here. But the input needs to come from the input list. As I look through this list, there are no 7s there now, but I can continue the pattern for a couple more and I end up with an input of 7. Now that was just continuing the pattern by continuing to add 1. Now on the outputs, you should notice that they do go down by 3 each time that the input goes up by 1. That does mean it has a slope of negative 3. But if we just continue going down by 3, negative 2 minus 3 is 5. And negative 5 minus 3 is negative 8, making T of 7 equal to negative 8. Now this is called extrapolating, where you use patterns in your data to go beyond. Extra is beyond or outside, and polate kind of refers to the points as far as I understand it. So they are points outside of our data. Evaluate K of 3. Now from a table, we have the X column, which is the input column, and the K of X, or output column. To do this, we need to take an input of 3, find it, see what the output is. In this case, it is 9. All right, K of negative 1. Now, the inputs do not have a negative 1 here, so I am going to have to use patterns to find it. As I travel up the table in this direction, I'm subtracting 2 each time. So I can take 1 and subtract 2, and it does get me to that negative 1 that I want. And as I go up the table on the outputs, it becomes 5 less each time, or subtracting 5. 4 minus 5 is negative 1. So K of negative 1 is negative 1. K of 9 is 24. It's just right there in the table. We can read it right out. And K of 8. Now we don't have an 8 in our input column, but 8 does come halfway between 7 and 9. So we are going to use the linear pattern to find it. Halfway between 7 and 9, so you want to find halfway between 19 and 24. This can be found 2 ways. One way is to do 19 plus 24, you get 43. divide it in half, and that's just finding the average. That's not the way I would necessarily choose to do it. You can do it more easily in your head by thinking about things in terms of slope. To go from 19 to 24 is increasing 5. Well, I only want to go half that far. 5 divided by 2 is 2.5. 19 plus 2.5 is 21.5. Anyway, this is called interpolation. We are interpolating by finding a point between. Inter means between, so it's point between. Okay, from a graph. When you have a graph, you're going to look at the input axis, which is your x-axis. Find 2 on the input axis. It's right here. And we need to know what the function is doing at 2. Well, here's x equals 2. The function's right there on the x-axis. Well, at that point, y is 0. So the output is 0. This actually represents the point 2, 0. P of negative 6. Okay, we want to go to negative 6 on the x-axis and ask what the function is doing at negative 6. It is right down here. That is negative 6, negative 4 is the point. So input negative 6, output negative 4. What we do is we take the input value, and that's our x. We go along the x-axis. We go out to our function and then find out what its y value, its output value is. Okay, let's look at P of 1. There's 1. It is just down a little bit from the x-axis. In fact, that is negative 0.5 or negative 0.5. And then P of 10, our graph does not go that far. So we're going to have to use patterns. There's a couple ways we could do this. One is to realize that at 2 it's 0, at 4 it's 1, at 6 it's 2, at 8 it's going to be 3, and at 10 it's going to be 4. So yeah, it will be 4. Another thing we could do, and 10's not a very big number, but if the number was like 100, you definitely want to do it this way, is to just create the equation and use the equation. It's got a y-intercept of negative 1, and it goes up 1 over 2. So we can actually create the equation, P of x is 1/2 x minus 1. And if we plug in 10, 1/2 times 10 is 5. And 5 minus 1 is 4, which is the correct answer there. By the way, P of 100 would be 1/2 of 100 minus 1, which ends up being 49. If you have to go way out there, it's probably better to create the equation, because the equation will take care of the patterns for you. All right, for the remaining examples, we're going to use these 4 linear functions. C of x is represented in the table. S of x is represented in that graph. V of x in the mapping diagram, and n of x is given as an equation. So let's evaluate n of 3. Well, first thing you want to notice is that n of x is the equation, so we're going to be using the equation to do this one. We're going to take n of 3, and we're going to replace the x with 3, so 3x becomes 3 times 3 minus 4. That, of course, is 9 minus 4, which is 5. Next example, C of 5. Okay, since it's C, we use the C of x function that's in the table. The input's 5, the output is going to be 26. C of 5 is 26 according to the table. N of 10, this again is using the equation. So we're going to do 3 times x minus 4, replacing the x with a 10. 3 times 10 minus 4 is 26. Now, we got 26 as our answer on that last one. So C of 5 actually equals N of 10. Later on in the unit, we're going to be talking about making comparisons. There'll actually be some comparisons we make today, but there are test questions dealing with these types of comparisons. C of 7. All right, if we look at C of x, look down the input list, there is no 7 as an input. But if we follow the pattern down, 1, 3, 5, 7 would be the very next number. Now let's try to find the pattern in the outputs. We go from 14 to 18 to 22 to 26. That is adding 4 every time. We can take 26 and add 4 and get 30, making C of 7 equal to 30. S of 4. S of x is in the graph. So we go to the 4 on the x-axis. It's right there. And we can travel up to the function. And it looks like 4 goes with 6. It goes through the point 4, 6. Remember that this is a way of writing an ordered pair. S of input equals output. Input 4, output 6. S of 4 equals 6. All right, true or false? C of 2 is greater than S of 2. So this is making a comparison between two different functions. First, C of 2. If we look at C of x, we're going to have to find 2. 2 is not in the list of inputs, but it is halfway between 1 and 3, so I can interpolate here. 18 and 22, halfway between is 20. So C of 2 is going to be 20. S of 2, right here is 2. It's just right there on the x-axis, 2 comma 0. So the output is 0. Is it true that 20 is bigger than 0? Well, yeah, that's true. Okay, another true or false. V of 2 minus 100 is 0. Well, V of x is my mapping diagram. V of 2 is 100. So this is 100 minus 100 equals 0. Well, that is true. 0 does equal 0. Okay, evaluate V of 10. Here's the input of 10. The output is 140. Evaluate V of 4. Here's the input of 4. The output is 110. Evaluate S of 0. We go to 0 on the x-axis and we find where the function is. It's right down here at 0, negative 6. So S of 0 is negative 6, which, by the way, is the y-intercept. When you plug in 0, you get the y-intercept. Which of the following is the greatest? C of 2, S of 2, V of 2, or N of 2? To answer this question, we're going to have to find out what these values are first. C of 2 we figured out a little bit ago is 20. S of 2 we also figured out is 0. V of 2 is 100. And N of 2 is going to be 3 times 2 minus 4. That's 6 minus 4, which is 2. So which of these are the greatest? It would be C, V of 2, because 100 is bigger than those other three numbers. What is the rate of change for S of x? Well, S of x is right here in the graph. Rate of change is the same thing as slope. It tells us how the outputs change compared to the inputs changing. Finding a slope from a graph, we tend to just do a little right triangle. This has a rise of 3 and a run of 1. If we do rise over run, we do get a slope of 3. So the rate of change for S of x is 3. That means the outputs are changing 3 times quicker than the inputs do. What is the rate of change for C of x? Okay, finding a rate of change from a table, we just need to find the changes in the outputs, which they are going up by 4. The changes in the inputs, they go up by 2. That gives us a change in output divided by change of input. That gives us a slope of 2. Which, by the way, we could write the equation for C of x. We just need to know what 0 outputs to, which right here, it actually outputs to 16. So C of x is 2x plus 16. Determine S of x. Well, we're going to find what S of x is. We need to know two things, slope and intercept. Slope we found a couple slides ago. And y-intercept is right here at negative 6. So S of x is going to be 3x minus 6. All right, let's determine N of h. Now this is N of x. This is actually just a variable change thing. We're going to replace x with h. So N of h is going to be 3 times h minus 4. And there's nothing more we can do to it than that. That's just a variable change. Now, N of 3D, everywhere there's an x, we're going to replace with 3D. 3 times x, so 3 times 3d minus 4. 3 times 3 is 9. So this is 9d minus 4, and there's no more simplifying that can occur there. Let's do v of x. To determine v of x, we need to find the slope. This is increasing by 10, while the inputs increase by 2. That gives us a slope of change in outputs over change in inputs, 5. The rate of change is 5. The y-intercept would be wherever 0 goes, which we can find with patterns here. As we move up the inputs, 8, 6, 4, 2, 0 is going to be the next one in that pattern. So I can do the same pattern with the outputs. 120, 110, 100. The next one will be 90. So the y-intercept ends up being 90. This gives us the equation for v of x of y equals 5x plus 90. Okay, just one more thing before going to the assignment, and that is that we can plug in an expression into a function. For example, h of x is 3x plus 4. What is h of x plus 1? Well, we're going to take 3x plus 4 and replace the x with x plus 1. And we just simplify this down. Now, what this actually does to the function is it's just going to do a little translation to it. It's going to move it. Anyway, this comes out to be 3x plus 3 plus 4. 3 plus 4, of course, is 7. So this ends up being 3x plus 7. H of x plus 1 will be 3x plus 7. K of 2x minus 3. Well, k is, first of all, I scrolled down too far, 3x plus 1, so 3x plus 1. And we replace x with 2x minus 3. Then we can distribute and simplify this down. 2 times 3 is 6, so 3 times 2x is 6x. 3 times 3 is 9, so 3 times negative 3 is negative 9, plus 1. Negative 9 plus 1 we can simplify down to negative 8. Okay, this last one has us do what's called a composition, which you should learn about later in your math schooling. But what we're going to do is take the h function and plug k of x into it. So h of x is 3x plus 4, but we're going to plug in k of x. So it's 3 times k of x plus 4. Now let's replace k of x with 3x plus 1, because that's what we are actually plugging in. And we can simplify this down by distributing. This is 9x plus 3 plus 4. 3 plus 4, of course, is 7. So h of k of x is 9x plus 7. Now, compositions of functions are useful if you need to apply two functions to something. You could do a composition of them and then only have to apply it once. For example, if you had a function that would discount an item for you and another function that would add sales tax, you could compose those two functions and have a function that would do both at the same time. All right, let's take a look at what's on the assignment. The first question has you decide whether they're functions or not. These are just quick yes/nos. Number 2, you're practicing using function notation on equations again. This time, though, we are going to be plugging in things like x plus 1, or maybe we'll do f of 2 and then add 1 afterwards. We might take two function values and subtract them. Number 3 is more function notation. You're going to find out what f of 4 plus t of 6 is. Number 4, you're going to graph two functions on the same grid. Number 5 asks a question about when the values are the same. It relates to something we've learned previously. Number 6, I give you an equation. I give you a circle, not a circle, a triangle actually, and tell you that its area is 15 square inches. You're told that that triangle gets rotated and asked what the area of the image is going to be. For that, just remember what happens to a triangle when you rotate it. Does the area change? Number 7, determine whether each of these situations is a function and give me a quick explanation why or why not. On number 8, you're given these 4 functions over here, t, k, h, and r. You're going to determine which of these 6 equations are true. Well, they're not all equations. some of them are inequalities. Which of these statements are true?